All right, I'm starting the recording. Are there any questions about the current homework assignment? The coding of how to convert a base 10 scientific notation with negative exponent so that you end up with a 64-bit coefficient, a 0 for the exponent of 10, and whatever is necessary for the exponent of 2. Are there any questions about that assignment at this point? No questions? All right. Well, I'm assuming you guys are on track, okay? I'm assuming you have already started on that project because it is not complicated, but you might want to give yourself plenty of time to write that code. All right. So without any questions about that, we're going to move on to talk about memory devices today. So we are technically done with this entire module. I did not really break down the module by a whole lot into smaller fragments. So the module, this entire module of physical states, gates, and numbers is now done. Okay, so we are basically done with. You want to put that up here? Yeah, yeah. So it doesn't use up your space. There we go. So what we are moving on to is what we call the von Neumann architecture. So now we are moving on to the next module, which is down here. And it's called von Neumann architecture and memory. So to understand the von Neumann architecture or von Neumann architecture, okay, so I think that's the more proper way to pronounce it. The first thing is, I kind of want you to understand who is von Neumann, and also, why the von Neumann architecture is actually important. So we're going to start with that. So we'll look at von Neumann first. Neumann, and here's the Wikipedia page of John von Neumann. It's a pretty long Wikipedia page. I'm not going to read the entire thing. And here is his the pronunciation of the name. And it doesn't, funny, it doesn't have a play button. So it's supposed to be von Neumann, I guess. Von Neumann.
I think it's von Neumann.
Von Neumann, right? Okay.
John von Neumann.
John von Neumann. Now, why is he interesting? It doesn't look that interesting. Well, the guy is a genius in many different STEM areas. He helped build the hydrogen bomb, which probably was, many people speculated that's the reason why he got cancer. And he passed away only when he was, let's see, what was his age when he passed? All right, so he was 54 when he passed away. And I will be 54 this year. And I have no plan to go just yet. But sometimes it's not going to be my plan or any person's any. It's not going to be my plan. But he died of cancer, and many people think that it had to do with the test explosions of the hydrogen bomb. So the other thing that is kind of interesting about him is he's not a physicist. He is not a mathematician. He is not a statistician. He is actually a jack of all trade and good at every single thing. So during his prime, if you ask anyone, of an area that he is good at, like specialists, okay, if you ask a mathematician and ask about their opinion of John von Neumann, they go like, he's a genius. If you ask the physicist, they'll say he's a genius. If you ask the computer science people, they will say he's a genius. So he is very, very interesting because he's good at so many different fields. So the list is right here. So everything from math and many different sub areas of math as well. Physics and many sub areas of physics, economics, general equilibrium theory, computing, and many different areas of computing as well, and statistics. So, okay, so that's kind of the background. I think he was was also teaching at Princeton when Albert Einstein was teaching at Princeton, so they kind of overlapped for a little bit of time. These two cannot be more different in terms of their personalities. Einstein was the quiet type who likes to kind of just kind of shut the door, be quiet, and do his research, do all his thinking. This guy likes to play loud polka music. I mean, he is Hungarian after all. So the two, probably had a lot of interesting conversations in Princeton when they overlapped. Yep.
I wonder if Richard Feynman was also there at the same time.
That I do not know. You can probably look up their time, when they were at Princeton University. But it was kind of interesting. And talking about Hungarians and polka dance, you can look up Hungarian dance algorithms. If you have not done so, I would advise you to do this at some point in time because they actually use Hungarian folk dance to demonstrate quicksort and other sorting algorithms, including heap sort and so on. So it's very entertaining because you can see all of these dancers. They have numbers on the back, and then they would do the Hungarian dance, the actual dance, and then they would just be shuffling around. But the way they shuffle around is reflecting, the outcome of the various sorting algorithms. So interesting stuff, not totally related to this class. All right. So what we're going to do now is to go click on one particular thing that he is good at, and it's named after him, which is the von Neumann architecture. So you look at the von Neumann architecture, represented by this picture. You go like, I don't see anything particularly interesting. You have an input device, and then you have the central processing unit, which is we call the processor these days. It interacts with a memory unit, which is basically the banks of memory chips in your computer, and it has an output device. You look at this diagram, go like, so what? I mean, this is exactly how computers ought to be. Well, we understand that as how computers ought to be only because computers have been like that since von Neumann came up with the von Neumann architecture. So think about updates to your cell phones, okay, in terms of the software, your apps, and even the operating system. Do you have to plug in your phone to a CD drive? Get the CD from T-Mobile or Motorola or Samsung or Sony, put the CD in, and then you have to kind of key in some special command. The CD would load the new operating system onto your cell phone. And is that how you update your cell phone? No? Okay. So in the past, before von Neumann, we can't even do that. Okay? In order to change the behavior of a computer, you have to open up the computer. The behavior of the computer is completely dictated by the hard wiring of how components connect to each other. So if you want to change the behavior of a computer, you have to rewire it. I mean, physically. We are not talking about virtual rewiring. We're talking about physical rewiring. Can you imagine the number of wires in a computer, even back in the 50s or the 40s? It's a lot. And then after you rewire the whole thing, you double check, right? You fire the thing up. If it doesn't work, well, good luck. Now you have to recheck every single connection, to make sure that you've made the right connections. But whoever gave you the wiring diagram to ask you, oh, we want to rewire the computer this way, that can be a mistake over there as well. Okay? So his contribution is to say this is unnecessary because computers already have memory at the time. Because in order to process data, the computer needs memory in order to say, okay, where's the counter? I need to count something. Or if you're trying to do an equation, it needs to store the result of the equation somewhere. So the computer already had memory. It was just not being used to store instructions or to specify the behavior of the computer. So memory was used purely and strictly for data purposes. The behavior of the computer was dictated entirely by physical wiring. He came around, okay, John von Neumann came around, and he said, what about using the memory also to specify the behavior of the computer. That was his contribution. The whole idea of using a memory unit or using the memory unit to also specify the behavior of the computer was his contribution in computer science. Without that contribution, we would not have cell phones. At least not the way you use them. Okay, your cell phone would still be a brick. Well, not necessarily a brick, but it won't be able to update itself. Okay, so his contribution is really, really significant. It's just that we have been living with the von Neumann architecture for so long that we don't realize, how things would have been if it's not for him saying, hey, we can actually try to use the memory to also store instructions and therefore specify how the computer is supposed to behave. Is that okay? So central to this entire idea is the memory unit and also other things inside the processor that will also be used to let the computer quote unquote run based on the instructions that are stored in the memory. Are we still doing okay so far with this kind of storytelling thing? All right? Because I think the background is really important that we understand how things become the way they are now. All right, so with that said, I am going to show you my specific von Neumann architecture using Logisim. So Logisim is coming back soon. Okay, maybe not right now, but very soon it's going to be coming back. So let me use the command line interface to run Logisim. All right, so we'll go change to, I'm not sure where I put it. Let's see. No, yep, nope, not here. So let me check out documents, CISP310. Yep, I put everything here. Okay, so you guys all remember Logisim. I certainly hope you remember. So we start up Logisim first, and then what I'm going to do is to start up processor 0004 because this is revision 4 of this processor, and see what happens. Because I do want to show you, it loaded in the other window, so I have to move it into this one. There we go. So this is the processor that you'll be using after the floating point homework assignments. Um, the thing is, most of this is actually the processor. The memory is only one component. This part here, that's the memory. The rest is the processor. Okay? So, but it does illustrate the von Neumann architecture, or at least the concept of that, because your code, or what specifies the behavior of your computer, is going to be stored in memory. The rest of the circuit, which is basically the entire processor, is going to be able to read from locations inside your memory, and then it will decode it using this particular decode engine. And then once it's decoded, it will basically tell all the rest of the components here how to behave in order to get something done. It looks a little daunting at this point, but at some point we're going to look at this, and I will tell you how to understand this architecture. You can download it already. Okay, right now you can actually go to the shared drive and download it, and if you want to play with it, you're more than welcome to. But there's no need to do that right now. But I do want to show you that this is what we're going to do. This is what we will be. This is what we will be doing for the rest of this entire semester. Are there any questions about this? So I am not using the x86 architecture because if you have friends who took this class from a different campus, they're all using the x86 architecture, which in my humble opinion is the worst possible architecture to use to teach this class. Yep.
What?
Sorry?
Can I ask why?
Oh, why?
Yes.
Well, where do I start? the X the x86 architecture uses what we call a CISC philosophy. So there's RISC versus CISC. CISC means complex instruction set computer, and RISC means reduced instruction set computer. So in the RISC design, They try to simplify the hardware, they try to simplify the number of instructions, and they try to simplify the number of addressing modes and whatnot. So the idea is they want the computer die size to be as small as possible, to use as few transistors as possible. CISC, on the other hand, is the opposite. They try to make one instruction or one addressing mode for everything that we want to use. Okay, so when you look at a compiler, you have a program written in C or C++, and you need to translate that into assembly code. So the CISC approach is to say, oh, I want to use as few instructions to specify the same program as possible. So one is trying to optimize the object code that is coming out of the compiler. The other one is trying to optimize the number of transistors on the processor die, which is basically the number of transistors on the actual processor chip. So the question is, which way is better, right? Now you have two opposite philosophy in terms of processor design. Which one is better? I can tell you the only reason why the x86 architecture is continuing to be used is Microsoft. Not even Intel, not even AMD. It was Microsoft. The reason why it was Microsoft is because Microsoft does not have a tool chain that is flexible enough to recompile their operating system, the applications and whatnot. So they cannot just say, hey, we want to transition to this new, really much better computer architecture, but they have so much code base that is completely based on the x86 architecture, they cannot move, at least not easily. Let me show you one more thing. So since we are on this topic, this is actually part of what this class is supposed to teach, which is CISC versus RISC architecture. So let me show you Debian, which is what I'm using right now. So Debian is a distribution of Linux. You can get different types of distribution with Linux. Debian is just one of them. But I want to show you a particular package. Okay, so we'll say Linux binary, Linux image. There we go, Linux image Debian. And that will give me this over here, but that's not what I want to show. Okay, let me pick another package. So we don't want to look at the image, we want to look at a particular application. So we'll go look at Zernal, okay, just because I use it a lot. There we go. All right, so when you look at Zernal, it will give you your different versions. I will pick the latest and greatest. It's called the unstable version, which by any standard is actually extremely stable. Look at the number of architectures supported. So they go from the alpha architecture, which is a very old supercomputer architecture, to the AMD 64, which is basically what is in every single desktop or laptop computer these days, to the ARM 64, which is the processor used in most cell phones, or at least the core of the processors in most cell phones, and all the other variants of ARM. I think ARM EL is a smaller ARM chip, so it has a smaller die size. It's more optimal for embedded applications. i386, that's the previous generation of the Intel x86 architecture. IA64 was the unsuccessful Intel version of the 64-bit instruction set. There's a long history behind every single one of these things. I'm not going to go into the long history of those things. 68K was the processor used by the older Apple computers. So the Macintosh computers used to use the 68,000 processors. Not too many people use that anymore. And then you have the MIPS family of processors. That is a Berkeley thing. Um, and then we have PPC or PowerPC. The PowerPC architecture is also very interesting. It is one of the few things coming out of the collaboration between Apple and Microsoft, of all things. So the PowerPC was supposed to be the super pretender of all processors. In other words, if you have a PowerPC in your PC, in your computer, you can use it to emulate the x86 processor, but you can also use it to emulate the 68,000 processor. So Apple would be using it to emulate the processor they used to use, and then Microsoft would push manufacturers to make it to emulate the x86 architecture. So this is the pretender of all the processors. And then IBM picked up, I take it back, it was not a collaboration between Microsoft and Apple, it was between IBM and Apple. And then we have the RISC V64. I'm not sure what that is. The S380X processor is a descendant of the IBM mainframe computers. Okay, so we are talking about vastly different types of architecture here. And Debian says, okay, well, as long as I have a GCC compiler to target that particular processor, I can use exactly the same source code, no problem. Now, every single operating system like Linux or Windows or Mac OS, there is a certain portion that has to be written in assembly, and that would be architecture dependent. But that should be a relatively small percentage of the source code. The majority of the source code should be written in C or something that is more universal. And that's how Linux was written. And that is also why Linux can be ported to all kinds of platforms with almost no overhead whatsoever. Is that okay? So the reason why the x86 architecture continue to exist and continue to be used a lot has to do with Microsoft refusing to move their products across different types of processor architectures, even though there are good reasons to do so. So now you guys will be asking, okay, what can possibly be a good reason to move from a CISC architecture to a RISC architecture? To answer that question, let's think about a LAN party scenario. I know you guys don't have to do LAN parties anymore because now we have, you just put on a headset, right? So now you can have teammates all across the entire globe. But then you won't be able to actually throw things at each other and really scream at each other, in high fidelity. So, just bear with me right now, okay? That you are trying to run a LAN party, okay? Let's just say League of Legends. Okay, so you have 5 people in a team. So you invite your friends over. They all haul their gaming computer over to your house, and the first thing you notice is when everybody power up the computer, the circuit breaker is going to pop. And why would that be the case? It's like it's just 5 computers, okay? Why would that pop a circuit breaker? How much power is one computer using? We are talking about gaming computers. So these are not laptop computers designed to run on battery for 10 hours. What is the usual power supply capacity for a real gamer's computer?
750, 800 watts.
Like 750 watts. 750.
7 to 800, yeah.
7 to 800. Okay, so that's just the power supply of the main computer, and then you have to add to it the monitor, which is not that significant, at that point. So let's just say it's 800 watts. Okay. Now you have 5 computers, right? 800 times 5 is 4,000, 4 kilowatts. So with 4 kilowatts, what is the amount of current that is needed? We're, we're talking about in the US, so the voltage is about 100. We'll just call it 100, so it's easy to calculate. So the current needed is the watt or the power in watts divided by the voltage, which is 100. So you got 4,000 divided by 100, which is 40. So that means your LAN party needs 40 amps. Okay? So you go to the circuit breaker. I encourage all of you, if you have access to a circuit breaker at home or at your apartment, go open up the circuit breaker and look at the rating of a particular circuit breaker. What is the biggest circuit breaker that you can find in a normal household circuit breaker or panel? 20 amps, okay? Most circuit breakers will pop at 20 amps. So in other words, you need 2 circuit breakers dedicated to only your room so that you can have your LAN party. Let's say your parents are rich and they are also very tolerant. They go like, fine, we'll get an electrician and rewire your room. Now we have like 3 circuit breakers going into your room just to be sure, right? What do you think is going to be the next problem? 15 minutes into your League of Legends games with all the screaming and whatnot, everybody is sweating, but not because of the game. Why do you think everybody is sweating in the room? Sorry? You got five computers running, but isn't all that power or the energy being used for computation? I mean,
My room is already hot, and I have only one computer. If I close my window and the door, it will be.
exactly. If you close your door in the summer, even if you have air conditioning vents and the AC is actually on, the central AC is on, you won't have enough cooling power to cool a room with only one computer. Now we have five gaming computer. So what is the wattage of a hair dryer? Oh, no, 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 no. No, with a 200-watt hair dryer, you can spend an hour. I mean, for those of you with longer hair, plan an hour to dry your hair. You might as well go out for a drive with the windows down. A hair dryer is,
I think like 1,200.
yep, usually about 1,200 watts, sometimes up to maybe 1,500. So that's only one hair dryer. Okay, you have what is equivalent to two close to three hair dryers, heating ability with five gaming computers. Then you go like, well, that doesn't sound too bad. I mean, I go to the bathroom and I take a shower and I need to dry my hair. Doesn't seem to heat up the bathroom all that much. Well, that's only because you use the hair dryer for what, 5 minutes, 10 minutes. We're talking about turning on all of these computers for at least a few games, which is an hour, 2 hours or so. Yeah, so your room is going to have so much heat built up that it will be intolerable. And this is an interesting problem, okay? Because this is exactly the problem that data centers are facing. So if you think about Google, think about Apple, think about Amazon, think about all those cloud services. They run gigantic data centers. The problem, the, the problem of trying to fit more and more processing power into one data center is not physical space. It is cooling ability. So, okay, so now we are not thinking about, oh, how fast is one chip? We are looking at to get a certain amount of processing done, how much energy is needed to get a certain amount of processing done. As it turns out, CISC is the wrong answer here. Why? Because a CISC processor has a lot of transistors, a lot of stuff, okay? But at any particular time, not really a whole lot of them are actually being utilized, but everything is consuming power at the same time. So the energy efficiency of a CISC processor is actually quite poor. A RISC processor, on the other hand, is trying to optimize the use of the transistors. And as it turns out, even though one instruction doesn't do nearly as much as one from the CISC processor, you need quite a few instructions to make up for one of the other one. From the energy perspective, it is actually more energy efficient. And that's why most data centers, they make use of RISC processors and not CISC processors. The x86 is a prime example of a CISC processor. So is that kind of giving you guys a general picture about CISC versus RISC? So that's kind of a useful part of this discussion. And what you saw earlier about text toy processor, which is this one here, is definitely a RISC processor. I did not take it all the way to being RISC because I found out that the way you have to write your program is extremely tedious when it's like that. So I did have to go a little bit off and go like, well, I'm going to allow these instructions, even though this instruction can be done by those two instructions, but because it happens so often, it pays off. All right. So that is that. So now the question is, um, how does the computer remember something? So that is going to be the next focus is, okay, give me the circuit that can remember something. So what I'll do next is, well, I'm going to stay in Logisim now that I have it up and running. But we're not going to take a look at the processor. Instead, we're going to look at a very simple circuit. So I'm going to make a new circuit here that is made out of two NAND gates. So I'm going to pick up a NAND gate, change the number of inputs to 2, and change the size to narrow. Make a copy of that. And I can magnify this a little bit. There we go. Pick up 2 input pins, one over here and one over here. Pick up 2 output pins, one over here, one over here. And we'll label the pins. I'm going to call this one S, and we'll call this one R. We'll call this one Q, and this one is NQ, which is not Q. Okay, and now we'll draw the wires. So here is how the inputs go to the input of the NAND gate. The output of the NAND gate goes to the output pins. Looks really simple, right? So here is where the fun starts. Okay, the output of one of the NAND gate goes to the input of the other NAND gate, and it is symmetric. So we take the output of this one, and then we feed it to the input of the other one. So this is the first time that we see a circuit where a component goes, we can form a loop, okay? So if you think about the digit 8, this is kind of like that, okay? It has this kind of thing going on. Because if you track down the connectivity, you can see how this pin goes to this gate. The output of this gate goes through this wire, and it goes into this gate over here. But the output of this gate also goes all the way back to the other gate. So the analysis of something like this is going to be a little bit interesting. This is called an SR latch. Okay, the SR latch is described in one of the modules on the website. So let me show you where you can find this, and then we'll continue to talk about the SR latch. This is where that stuff is. Okay, D flip-flop and other basic memory devices. So if I go there and click on the link, now we get to see this is the SR latch, but expressed in text. So we'll get there and talk about that later on. Not too concerned about this, okay? I want to give you the pictorial representation first. All right, so looking at this, you go like, how do we know what it is supposed to do, right? That's going to be a little bit difficult. So what we're going to do is to look at this, and we want to figure out what happens when we change the input, or given a particular configuration of the input, what this device is supposed to do. So that's the first thing we are going to do today, is to just kind of analyze or figure out how to analyze a circuit like this and try to figure out its behavior. Are we okay so far? Okay. So the first thing I'm going to do here is to disable simulation and reset simulation. So this way we don't really have specific values to look at, and that's intentional because I want to analyze, or I want to learn how to analyze this circuit here. The other thing I'm going to do is to label this as N1, which is the first NAND gate, and this is going to be N2, which is our second NAND gate. So this way I can refer to each component explicitly without any ambiguation. All right. So we're going to analyze what happens when both inputs are zeros, okay? Because that's the easiest one to analyze. So we'll go ahead, and I'm going to use a text editor to do this analysis. And the recording is on, I just want to make sure. But this is all described in text in the module, so you can just kind of focus on the discussion and ask questions when you have something, when I'm not 100% clear about something. All right, so I'm going to use Mousepad, which is just a regular text editor. I'm just going to stash it over here so that I can do the analysis. So I'm going to state this is example 1. And the initial condition is we want the S input pin to be a 0 and the R input pin to be a 0. All right, so what are we going to do next? So what you need to do is to look at the connectivity of the circuit, and you ask, what component is going to be immediately affected by the configuration of the S pin being a 0 and the R pin being a 0 as well. Okay, I think we have two components that can potentially be affected, right? One is N1 and one is N2. So the question now is, because S and N1, the first input of N1 are connected, so I'm going to use this notation to specify the first input of the NAND gate N1. Is that okay? I'm simply borrowing the indexing operator in C++ to basically specify, hey, if you have a bunch of input pins, this is how I designate which input pin I'm referring to. Is that okay? Is the notation okay? All right. So the first thing we know is, well, this one is connected to the S pin, and therefore it's getting a value of 0. N2 dot in bracket 1 is R, which is also 0. Okay, well, that part I think we can get, right? Because to figure out this part only has to do with analyzing the circuit itself. Where is this Y going to? Okay, not a problem. But the next part is, I'm going to say after a propagational delay. Now, this is really important because from the moment the input of a gate is changed, it takes a little bit of time for the output of the gate to change to reflect the correct calculation of the gate. Okay, so there's a propagational delay before the output of N1 and the output of N2 would change corresponding to the change of the input pins. Are we doing okay so far with that concept? There's a propagational delay. Okay, so after a certain propagational delay, can we say something about the output of N1 and the output of N2? So let me just kind of put these as question marks, and then we'll try to resolve the question marks. Some of you are going to go say, but this is circular, okay? Until we know what is the output of N1, I have no idea what the other input of N2 is, and therefore I cannot determine the output of N2, and vice versa. Because until I know what is the output of N2, I won't know the other input of N1, and as a result, I cannot tell what is the output of N1. Well, that may be the case, okay? But it depends on the gate that we are talking about. What kind of gate are we talking about? What is N1 and N2? What is the type of that gate? It is a NAND gate, right? So when you look at the truth table of a NAND gate, do you think we can know the output given that one of the input pin is known to be a 0 already? What would be the output? Yep, both of them. In other words, we really do not need to know what the other input pin is, but by knowing just one of the input pins is a 0, we know for sure the output pin is going to be a 1. All right? Now, this is really important. What is important is not the fact that we know now that the outputs of both NAND gates are 1s. The important part is how did we figure it out? One way to look at this is a truth table. Okay, so I'm just going to show this once so that you guys can kind of hopefully remember that. So this is X NAND Y. So when X and Y are both zeros, X NAND Y is a 1. If X is a 0, Y is a 1, the output is also a 1. That is also a 1. The only time the output of a NAND gate is a 0 is when both inputs are zeros. So you look at this, and then you say, well, if we already know one of the inputs, it doesn't even matter which one is a 0. Hey, if X is a 0, the output is guaranteed to be a 1. If Y is 0, the output is also guaranteed to be a 1. So that means if I just know one of the input pins of a NAND gate is a 0, the output is guaranteed to be a 1. I don't even need to care about what the other input pin has to say. Is that okay? So this is an application of a truth table to visualize why I can make that deduction that I did make a little bit earlier. Are we good so far? So the reasoning part is far more important than the actual conclusion of, oh yeah, we know both outputs are ones. So I hope you guys are getting that. All right, so if the outputs are ones, then we also know what the output pins are going to be reflecting, because Q is the same as N1.out, which is going to be a 1, and then NQ is N2.out, which is also a 1. Woohoo! Okay, we are done with the first example. Are there any questions about how I went about the analysis of the circuit and came to the conclusion? No questions? Okay. So technically speaking, I really should have a few more steps. Okay, so technically speaking, I'm going to have to say, well, since we now know what is the output of N1.out and what is N2.out, now we actually say, okay, now we know that N1.in bracket 1, which is the same as N2.out, and we know that is 1. And likewise, we can now know that N2.in bracket 0 equals to N1.out, which is a 1. But this does not cause any additional changes, because no further changes at this point, because changing the other input pin or knowing what the other input pin is for N1 and N2 doesn't change the output, because we still have that one pin of 0, one input pin of 0 for each of them. So there are no further changes to analyze at this point. We have reached what we call a steady state. A steady state simply means there are no additional changes, because the circuit is now at a point where everything is quote unquote consistent. Are we okay so far? All right. And I know some of you are really thinking already, because if there is such a thing called a steady state, what is the implication? Exactly. So there are certain configurations of things are unstable. You do not arrive to a steady state. So we'll talk about that. Well, let's go there first, okay? Because I'm going to change up the order a little bit in this class and go for the unstable configuration. Okay. So the unstable configuration is going to be example 2, which is following example 1. Okay, so do this right after example 1. So we have to do example 1 first, and then this is example 2, where we change both S and R at the same time to 1. Okay? You're like, okay, so what's going to happen? Well, we're going to look at from the perspective of the gates. Now remember, there's a propagational delay. So that means the most immediate effect of changing both input pins to ones is this, okay? It's really easy. This is now a 1, and this is now also a 1. So from the perspective of both N1 and N2 gates, what are the configuration at this point? So let me just relist everything. What was N1.in bracket 1? In other words, what was the state of the second input of N1 coming from example 1? It was a 1. Okay.
Wait, so is this the cycle after like what we did on top there?
Yes.
Okay.
And what about N2.in bracket 0? The first input to N2 from before, what was it? What we deduced it was a 1 before, right? So now we know both inputs of N1 and both inputs of N2. If you remember from the truth table earlier, what would be the output of N1 and N2? We got both input pins of a NAND gate being ones. So the output is going to be a 0, okay? But we're going to have to say after a propagational delay. I'm just going to use a PD to abbreviate that. So after a certain propagational delay, we say N1.out is going to be a 0, N2.out is also going to be a 0. But that is not the last step. because we know that n1.out goes to the first input of n2, n2.out goes to the second input of n1. That's just because of the connectivity of the circuit. So right away, we can now say n1.in bracket 1 is also going to be 0 because it is the same as n1.out, n2.out, and then n2.in bracket 0 is also going to be a 0. Is that okay? All right. And so the other input pins would continue to be the same. In other words, um, n1 dot in bracket 0 because it's connected to an input pin. That input pin is still a 0, okay? And then the other one is, oh, it's still a 1, sorry. I forgot that we changed the input pin already. So let me do this to remember that because I forgot to change the picture. So I was looking at the picture and thought that they were still zeros, but they're ones now. Okay, so now we also can say n2 dot in bracket 1 is a 1. Okay? Are we doing okay so far at this point? How I came to the conclusion about both input pins of n1 and both input pins of n2. Are we good so far? Okay. But this is a change to the input pins of the NAND gates. So I do need to say after propagational delay, let's see if it is going to change the output of the NAND gates. What do you think? What is going to happen to the outputs of the two NAND gates? Are they going to change or are they going to keep the old state and we are pretty much done with this entire analysis? What is the truth table telling you? If if one input of the NAND gate is a 1 and the other one is a 0, what is the output of the NAND gate in that case? It is a 1. But is that a change from what it is currently? What is the current output of the gates? The current output of the gates are currently 0. After a certain propagational delay, they both become 1s. So n1 become n1.out is now a 1, n2.out is also a 1. Oh, okay. So if the output of a gate has changed and it connects to something, to the input of something else, we are not done yet. Because now we have to follow the wiring and say, hey, this has changed. Let's see where it leads to. It leads to the input of this guy, so we can potentially be changing the state of this guy here. What about this thing? It just changed too. So we follow the wiring, it goes to the input of another gate. So now we have to continue the analysis. Or do we? Have we seen this state before? That both outputs of the NAND gates are ones. That was the initial condition of example 2. In other words, we are now back to where we were before. So that means this entire circuit is only going to alternate between this state and this state. In other words, the outputs of N1 and N2 will simply alternate between 0 and 1. So it's going to go 1 and then 0 and then 1 and then 0. The amount of time that it stays in each state has to do with the propagational delay of the logic gates. So if the propagational delay of the logic gates, meaning how much time it takes for the input to become effective, if this is like 5 nanoseconds, then we're going to see 5 nanoseconds of 1, 5 nanoseconds of 0, 5 nanoseconds of 1, 5 nanoseconds of 0. There is no steady state in this case. Is that okay? And you might be thinking, can we do this in Logisim and actually see it not being stable? The answer is yes. So the way to do this in Logisim, because I do want to teach you this, because I want you, for those of you who are curious, to actually do this yourself and go like, oh, so Logisim actually does understand the concept of steady states. So to do this in Logisim, the first thing we need to do is to get rid of one of the input pins and just have the other one to connect to both of the input of the NAND gates, because this is the only way I can guarantee that they both change at the same time, because I can't click quickly enough to be quote unquote simultaneous. Okay, so with this, I can now reset one pin to 0 because that was the initial state, and then I re-enable simulation. And the moment I click this, it's going to start the oscillation. Okay, so we got 5, 4, 3, 2, 1. And Logisim is smart enough to detect that oscillation apparent, which basically means we do not have a steady state. Such is life. If life reaches a steady state, I'm not really sure I would like it either. I mean, we have a lot of non-steady state, the sun rising and the sun setting. Do you want the sun to be always like at noontime, or do you want the sun always to be gone? I mean, that would not be good. Just ask anyone living in the Arctic Circle. You don't get your vitamin D, and then you get too much vitamin D, and then you don't get your vitamin D. Anyway, so so this is a rather interesting circuit, right? So let me just undo the changes, get it back to where it used to be, and then simulate again. Not sure whether it resets itself. Oh, it does. Okay, very good. All right, so the moral of the story is you don't want to change both input pins from 0, 0 to 1, 1. Okay, so if we are not going to do that, what else are we going to do with this circuit? Change one at a time. Okay, it's okay to change one input pin at a time. You just don't want to change both of them at exactly the same moment, from 0, 0 to 1, 1. Is that okay? All right. Okay, so now I'm going to take out example 2, or I can just kind of put this all the way down. So I would just say example 2, this is 2b, okay, because I want to give you another example 2. So get it out of view, okay? And now we have another example 2, the actual example 2. Let's call this 2c because I'm going to have 2 more. Uh, this is 2c. So we'll call this one 2a. All right, so in example 2a, we are changing one pin at a time. So in this case, I'm keeping S to be 0, but I will change R to a 1. Is that okay? So in terms of the actual circuit, let me turn off the simulation. This is the second state. Okay, it's following example 1. I'm only changing one pin at a time, where only R is changed from a 0 to a 1. So I first want to make sure that everybody understands what I mean by I'm only changing one pin at a time this time. But this entire thing is after example 1. Are we okay so far? All right. Okay, so let's do some analysis. The first thing is, well, since the input pin S is not changing, I'm not going to look into N1 because, hey, it's not being changed directly. So my only concern here is N2. So we now look at N2 and go like N2 dot in bracket 1 is now a 1. That is the first change from the perspective of the logic gates. Are we good so far? All right. So in the next cycle, okay, after a propagational delay, I'm only interested in N2 because N1 has not experienced any changes whatsoever. So my only concern is, well, is the output of N2 going to change in any way because of the change of the input pin R? So what do you think? So the first thing we want to know is, okay, tell me what is N2 dot in bracket 0 and tell me what is N2 dot in bracket 1 because I need both of those to understand how N2 dot out might be changed. So what is N2 dot in bracket 0? From before, it's still a 1, right? And then N2 dot in bracket 1 is an input pin. It just got changed to a 1. So combining these two, can someone tell me what N2 dot out is going to be? going to be a 0. Okay, but is that a change from before? Did n2.out changed? Is it changed from example 1? So if you look at example 1, the conclusion from example 1 is both outputs are 1s. So indeed, we have changed the output of n2. Okay, so I'm just going to comment here. This is a change, right? Because every time there is a change, you're not done yet. Because now you have to track down where n2.out is going and whether that can potentially cause a change of something else. Does that make sense? Because what you're doing is you're looking at the blah, blah, blah. You're looking at the dependency between the components. This output connects to that input. This input connects to that output, and so this output connects to that input, and so on. So we are basically using the dependency of the circuit diagram to determine if this is changed, what else do I need to track down and see if this change is causing a ripple effect of that thing also being changed. Is that okay? So once again, the actual detail of how an SR latch works is important, but more important is the way that we are analyzing it. So the focus is two-folded. The first focus is exactly what an SR latch is and how it gets its job done. That's one. But the second one, which I think is more important, is how we use the dependency of the logic gates as described by the circuit to figure out if one thing changes, how do we track down what potential things would also change as a result of that? Is that okay? Okay. So now we look at this and go like, okay, n2.out connects to what? n2.out connects to n1 dot in bracket 1. So that is also now going to change. This is change. So every time the input pin of a device is changed, you need to analyze what happens after a propagational delay, because that can potentially change something else. So now we say after a propagational delay, the device that I need to analyze in this case is going to be N1, because after all, N1 just experienced one of its input pin being changed. So as a result, I have to ask the question, is that going to change the output of N1? But to figure out whether that's going to change the output of N1, I want to be reminded about both of the input pins of N1. So what is N1 bracket 0 at this point? It's still connected to the input pin, which is a 0, right? Okay. And N1 dot in bracket 1 was just changed to a 0 as well. So now I know the entire thing about N1, both input pins, certainly enough to tell me what the output is supposed to be. So N1 dot out is going to be what? It's continuing to be 1. That is not a change from before. So let me just write this out first, and then I'll comment this is not a change. Why is it not a change? Because it was a 1 to begin with. I'm too short to point that, and I don't have a stick or a laser pointer, so I'm just going to use my mouse pointer to point all the way back to here. Is that okay? So this is where we can stop, because even though N1 has one of its input pins being changed, but the output is not changed as a result. In other words, we have just hit a dead end when it comes to change propagation, because at this point, there are no further changes to analyze. Things are now saying, okay, this is the same as before. Are we good so far? Yep.
And this is with the 0 and 1, like it stops, but with the 1 and 1, it does not stop. It keeps doing
That is correct. So if you change one pin at a time, it stops. If you change both pins at the same time from 0, 0 to 1, 1, it doesn't stop. It starts an oscillation. All right, very good. Let me just ask you a question. If one of you, went out to buy two P transistors and two N transistors, I don't even know where to buy the transistors these days because Radio Shack is gone. Um, HSC is gone. HSC used to be. Do you guys know where's Noble Vegetarian Restaurant? Yeah. So HSC was a company that used to be kind of not right next to it, but close by, and they sell surplus parts, and they also sell like individual transistors and resistors and whatnot. They are long gone. um, Fry's is gone. So I don't even know of a place in town that would actually sell individual transistors. The best place to get a transistor is on campus. Go to the ET or Electronic Technology Lab. I'm not really sure how they are relocating that lab because the whole area is getting renovated. But they would have transistors. I'm not sure they would just give you the transistors though. So let's just say that you use transistors, 4 for this one and 4 for this one, and actually build this circuit. And then you tie the input pins to be like this, and both of these input pins to be tied to exactly the same input pin. And then you hold that input pin to ground, which is the negative terminal of a battery, and then you transition that to a 1. I'm not sure how you can do that like right away with no events in between, but let's just say that you can do that. The output, if you hook it up to an oscilloscope, do you guys know what is an oscilloscope? Yeah, you would actually see the square wave.
Changing voltages.
It would just be oscillating between whatever the supply voltage is and ground, which is 0 volts. You can actually visualize and see it. So I just want to make sure that you guys understand that this is not theoretical. This is not just virtual. If you actually build a circuit, you can see the oscillation on an oscilloscope. Yep.
Square wave is like the one that goes like this.
Yeah, it's well a square wave is just basically this.
Oh, it doesn't go.
Yeah, that's a square wave. So in this case, it's going to be 0 volts, down here, and this is just going to be whatever the supply voltage is. So most logic parts are 5 volts or 3.3 volts if you get the individual transistors. So there we go. Okay. All right. So now we look at example 2A, and then we go like, okay, we want another example. So this time we have example 2B, 2B, where we are still. This is right after example 1 again, except this time I changed S instead of R. So R maintains its 0 and S got changed to a 1. So I think I'll leave it as an exercise for you guys to go through the propagational delay analysis, but I'm just going to say the circuit is symmetric. In other words, if you are to put a mirror right along here, the circuit is symmetric up down. So that means this ends up dot dot dot. It ends up Q being a 0 and NQ being a 1, whereas example 2A ends up having Q being a 1 and NQ being a 0. Is that okay? So here's the fun part. What if I change, after either 2A or 2B, that I change both input pins to 1s? Okay, so we'll examine that, okay, because I think this is going to be the fun part, which is really important in today's lecture. So we'll start with 2B. So 2B, then we go to example 3B, where S equals to 1 and R equals to 1. All right, so how do we do this analysis? I want to kind of do this a few more times so that you guys get a hang of it. The first question is, what got changed? So compared to 2B, 3B only has one input pin being changed, and that would be R. It's going to be R, okay? So we notice that R is changed, and R connects to N2 dot in bracket 1. So that is also changed to 1 because it was a 0 before. And as a result, after a propagational delay, I need to ask the question of what is n2.out now? Because one of its input pins got changed, so I need to kind of check and see if it is going to be changed. But in order to answer that question, I have to ask what is in0 for n2 and what is in1 for n2? Well, let's check. n2.in bracket 1 is the easy one because it connects to the input pin R, so that is the easy one. And then the other one, which is n2.in 0, well, that is just whatever Q is, because if you look at this pin here, that just connects to Q itself. And so we just have to figure out what Q was. Q was a 0, like so. So now we have to look at the input values of both input pins of N2 and try to figure out what its output is supposed to be. What is the output in this case? It's going to be a 1, right? Okay. And once we determine the output of a gate, then the next question is, did it change from before? In other words, comparing n2.out being a 1 in example 3b, is that a change from 2b? Well, 2b came to the conclusion that nq is going to be a 1, and so n2.out would have been a 1. So this is not a change. So we'll just comment this is not a change. And because n2.out did not change as a result of R being changed, this is the dead end, okay? We have now concluded. So none of the output pin is being changed at example 3b. The conclusion of example 3b is NQ, Q continues to be a 0, and NQ continues to be a 1, just like before. Are we good so far? So now we go back to example 2a. So we look at the end of example 2a, and then we come up with example 3a. So example 3a is going to do the same thing, where we changed the one pin that was a 0 into a 1. So in this case, let me look up the input pins. So this time S is changed to a 1, R is remaining as a 1. This is the one that is changed. Is that okay? Is everybody following, the example 3a is following example 2a? Okay. So in this case, we have to do the same analysis. We basically ask, okay, which gate's input got changed? Well, because S got changed, it connects to the first input pin of N1. So now we have to note that N1.in bracket 0 is changed to a 1, just because it is wired directly to the input pin S, right? And then we say after a propagational delay, we have to analyze what is the output of N1. Well, I cannot determine what is the output of N1 unless I know the inputs of N1. So let's see if we know the inputs of N1. It has 2 input pins. So we'll work with one of them at the same one at a time. N1.in bracket 0 is connected directly to the S pin. So we know that one is going to be a 1 for sure. What about the second input pin? The second input pin of N1 connects to N2.out. So now we have to look up example 2a and see what it used to be. In N1.in bracket 1 was a 0. Okay. So now that we know that the top input pin is a 1, the bottom input pin is a 0, what would be the output of N1 at this point? It's going to be a 1, okay? So now we say that this is going to be a 1, and every time an output pin is changed or figured out, you have to ask the question, did it change from what it used to be? Because not every single input change is going to result in an output change. So the question is, well, we noticed that the input pins of N1 got changed, but is the output pin changed as a result of that? So now we have to look at example 2a, and we ask, what was the output of N1? It was a 1. It is continue to being a 1. It's continuing to be a 1. So as a result, there is no change. Are we okay so far? Okay, so we are in the middle of a forest at this point. Okay, it's kind of hard to see what is going on. So I'm going to kind of summarize what we did up to this point. Okay, so I'm going to go all the way down here and we'll summarize. So we have two scenarios. We have S, R, and then Q and NQ. So in the first scenario, both started off as zeros, and then both output pins turn out to be ones. And I'm not really remembering which one is which one, so let me look it up because I want to be consistent. So in example 2, the A sequence is turning R to a 1 first. Okay, so turning R to a 1 first. There we go. So I'm going to comment here and say this is the A sequence. Put A in quotes, or sequence A if you want. There we go. So the conclusion of this is Q continues to be a 1, but NQ becomes a 0. And then we turn both of them to 1s, and none of the output pins got changed. Is that okay? Now you can kind of dig up what we did earlier and come to that conclusion, but this is just a summary of how the changes of the input pins affect the output pins without the explanation in between. So that's the A sequence. The B sequence starts off with S and R both being zeros. And as a result, Q and NQ are also both ones. In other words, with the B sequence versus the A sequence, the initial state were exactly the same. But this time with the B sequence, we changed the S pin to a 1 first and let the R pin remain to be a 0. And as a result of that, Q became 0 and NQ became a 1. And then we changed both input pins to a 1, which did not end up with any changes to the output pins. So the output pins of Q and NQ remain to be 0 and 1. So looking at sequence A and sequence B, do you notice something that is odd that we have not seen in all the other circuitry that we have talked about at this point? The state of the Q and NQ is no longer completely determined by the state of the input pins, at least not at that moment. Let me highlight what I'm talking about. When both input pins are zeros, both output pins are ones. Not a problem. It is consistent between the two sequences, right? That's okay. The second step is different, but then you can say, well, that's because the input pins are different, so we can expect the output pins to be different as well. Not a problem. But look at the third step. In the third step, both sequences end up with 1, 1 as the input, but yet the output are different. Does everybody understand what I'm trying to emphasize? It remembered.
If you make both of them the same, it'll keep the previous state. And it'll just
Exactly. Yep, that's exactly what is happening here. When the input pins are both ones, it is basically saying, oh, just maintain your previous state. Unless the previous state is having both inputs being zeros, that would be a bad thing because that starts the oscillation. So now we want to say, so why are the pins labeled the way that they are? S is the same as setting, R is basically reset. But I have to put a slash before that because they're active low. In other words, if the S pin is a 0 and the R pin is a 1, that means we want to set the Q pin. Setting means turning something into a 1. Reset means to turn something into a 0, but they're active low signals, which means when the corresponding input pin is a 0, that asserts what we want to do. When it is a 1, it is saying, we are not doing anything. So when both input pins are 1s, we are neither setting nor resetting. But when one of them becomes a 0, that becomes an action because we are now specifying, hey, I want to set that pin. Okay, I want that pin to become, or I want to reset. So the set versus the reset is relative to Q, and Q is just the negation of Q. So one of them is not typically really useful. So most circuitry will only bring one of the pins out and not the other one. Are we good so far? So this is the most basic memory circuitry in a computer. It is called an SR latch. Now, is it easy to use? No, this is not easy to use at all because you cannot just say, oh, this is a 0, remember it, or this is a 1, remember it. You basically have to say, if I want to change it to a 1, if I want to change Q to a 1, I have to turn the S into a 0 and then bring it back up to a 1. If I want to change Q to a 0, then I have to change the R to a 0 and then bring it back to a 1. Okay? So not exactly easy to use, but nonetheless, it has the effect of being able to maintain, quote unquote, the current state. Is that okay? Now, I do have to admit, the first time I came across this circuit, I was thinking, that is really smart. Because I would not have been able to figure this circuit out. Hmm?
From scratch.
Yeah. Yeah, go ahead.
I just want to ask something. Is Q a negation of S?
Is Q a negation of S?
Because if I'm looking at the truth table, it looks like Q is a negation of S.
Not always.
Not always.
No, not always.
So unless both are 1.
Right. So it's not exactly like that because if you look at this row here, it is not a negation. And if you look at this row here, it is also, oh, they are negations here, but the other one is not a negation.
Yeah,
so when you look at it here,
except the one where both are 1s.
Right.
But the rest of the time, it looks like there is a negation.
Yes, that is true. Because that has to do with the property of a NAND gate. If one input is a 0, the output is guaranteed to be a 1. That is why it seems to be a negation. Except when both are 1s, then it just maintains the state. Whatever it was, it would just say, okay, we're not going to change it. We'll just go ahead and maintain that state. All right, so now we are out of time for the lecture. I do want to show you what you should be reading over the weekend. Once again, I really have no idea whether you guys are reading or not. I can only keep nagging you and emphasize that it is important to do that. So we are basically done with the SR latch discussion. And this is just basically doing the same thing, except it is a very boring way of using just text to describe the whole thing. And this is the table. NC stands for no change, which is also described in the text itself. So we are done with the SR latch. The next thing is going to be a D flip-flop. So I want you guys to be able to read the D flip-flop section at least, okay, over the weekend before we meet again next Tuesday. Because if you start off reading this, at least be able to construct a circuit. Oh, this is one thing that I didn't talk about. Okay, so looking at the text description, how do you make the circuit, right? Well, the first part here, if you think about a circuit, this is basically telling you what you need, what components you need in the bin, okay, in the tray. So we need to go to the stock room to pick up a NOT gate. We need to pick up 2 NAND gates. We need to pick up an SR latch. We need to pick up 2 input pins, and we need to pick up 2 output pins. So this is just a part list, okay? In industry, this is called a BOM, or bill of material. Okay, it's basically a part list of, okay, what do we need? The rest of the description is telling you how we make connections between the components. So I'm going to pick one as an example. This here is basically saying, okay, let's make some connections. What connections are we making? We are looking at n.in. N itself is a NOT gate, has one single input. We look at n1.in bracket 0, which is the first input of the NAND gate n1. And then we also look at d.pin. D is one of the input pins, so it only has one connection point. And then we say, let's hook them, let's hook them up together, which is the same thing as drawing a wire between the components in Logisim. Is that okay? So this is a textual way to describe a circuit. Why do I want to use a text method to describe a circuit instead of using Logisim?
So we can like go ahead and replicate it.
Okay, so it's easier to copy and paste, for instance, right? But I can also write code to generate this. Do you guys still remember the carry look ahead equation or the generator? Do you want to do that by hand and then just copy from your napkin to the code that specifies the logic of your processor? Probably not, right? But if I give you the double loop structure and whatnot, do you think you can kind of write a program to generate that circuit? Probably, right? Because from the coding perspective, if you know how to write the code to do K3, K64 is going to use the same code. The output is horrendously complicated, but it doesn't bother you because it is just a subroutine. One of the parameters specifies which K are we trying to figure out. Instead of 3, it's 64. It cranks out the description of the circuit automatically. Okay, so related to this topic, some of you may find it useful. Some of you will go like, I'm not going to do this anymore after this class, but that's okay. So related, yeah.
So are we programming like every circuit we do?
No,
No?
I'm only using this as an example.
Okay.
So there is a language called VHDL, which is a hardware description language. There's another one called Verilog, which is also a hardware description language. So these two are the industry standards for describing circuits. If you go to Berkeley, okay, I'm not sure how many of you plan to transfer to Berkeley. At Berkeley, the last semester of the entire ECS, or Electrical and Computer Science program, involves the design of a processor. And it's not going to be something like my toy processor. It's going to be far more complicated. And that is going to be specified. I cannot remember which one it is, Verilog or VHDL, but it's described in one of those two. So if you want to become a computer engineer, someone who's going to design the gate logic inside the processor, or a GPU, right? If you work for NVIDIA, you might be working on a GPU. Or if you work for a cell phone company, you may be working on a very custom hardware just to do the voice coding, compression, and whatnot. If you work for Samsung, you may be working on an ASIC chip, an application-specific chip to do Bluetooth, earbud, noise canceling stuff, right? Most of those are going to be specified in one of these languages. Nobody in industry is going to do stuff like this or this, okay? If you think about the number of components inside a processor, this is not going to be a good way to do it. Now, why do I do it in this class? Because this way you can graphically and visually follow the lines and literally understand how things connect inside the processor. It's for educational purposes. But in industry, everything is going to be described in text, some kind of programming language.
I wonder how they then like design a circuit using the code. I wonder how they like get that done, or is it like automatically generated by the compiler?
Yep, there is such a compiler. So the compiler takes your text description that looks like C programs in a certain way. It will quote unquote compile the code, and it will first come out as gate logic connectivity. So that's not going to be sufficient to make a processor chip, because you have to further quote unquote compile the gates into transistor configuration. And that process, when I was in industry, was a black art. So there are things that you can tweak to try to make things happen. And then there are certain designs that you can represent like this, but it cannot be cannot be fabricated. So it's an interesting thing. I mean, I'll bet you can find examples online. So if you go to any search engine and you just look for processor HDL example, um, I'm just trying to see if they have the actual code in it. Okay, that's the ALU. And by the way, the toy processor also has its own ALU. It's not in the same kind of description. So anyway, so somebody just finish this entire design and have the whole thing working in simulation. But I'm looking for the source code. I'm looking for the actual code. Uh, well, those are snippets. Yeah, those are snippets of the code.
That's a surprisingly C-like.
Yeah, they are. They're high level code. You can use loops, you can use conditional statements. There are functions. So functions are basically used to crank out subcircuits that have similarities. Um, basically, you're writing programs.
That's pretty cool.
Well, it's necessary. Okay, I want to before we end today's lecture. Okay, which is to ask number of transistors in um, i7 processor. And that's the eighth generation, right? That's the eighth generation, which is what I have on this computer. This computer is 4 years old, and it only has 3 billion. Okay, okay, because I was thinking million is like, that's not a whole lot by today's standard. 3 billion transistors. The entire Earth has less than 8 billion people. So think about that. Yes.
How do they um, make them that small and then connect them all? It's just
Well,
so
the,
much.
the the whole process of making a processor chip is on by its own, an engineering field. They have to use not visible light anymore to do the specified, which part of the semiconductor material to etch away. I don't even remember what they use these days to specify the circuitry, the shape of the circuitry, like the wiring, quote unquote wiring. But I do want to point this out. This is horrendously outdated. 14 nanometer process is way old, like me. What is the current process? What is the current transistor size of chips rolling off the production line now?
Like
7 nanometers.
5 nanometer. Yeah, we're down to five now.
Yeah.
Yeah, the M1 chip from Apple, they're all using the 5 nanometer process.
We're getting to the point where we can't get any smaller. That's why we're doing quantum computing now.
Well, every time we thought we could not make things smaller, somehow they figure out a way to do it. Now, I can tell you this story. It's, once again, it would date me because it would tell you how old I am. When I was in graduate school, my roommate was a double E. When we played video games, in the computer lab, his call sign was submicron, which basically means at that time, people thought that it would be impossible to make transistors smaller than 1 micron. 1 micron is 1 micrometer. There are 1,000 nanometers in 1 micrometer. So in the 90s, people thought the transistor size cannot be reduced below 1,000 nanometer. And yet here we are. We are now down to 5 nanometers. So yeah, they will figure out a way because there's money to be made. As long as there's money to be made, someone's going to figure out a way.
The reason I was given is that they're getting to the point where quantum, like
Effects.
uncertainly start
Yep.
hitting. So electrons, instead of like going through the transistor and stuff, they'll
Yep.
just like decide to skip the transistor.
Well, okay, so the transistors, they're called FETs or FETs for field effect transistors. So they have an insulation layer in here, and then there's another substrate material here. So this is supposed to be an insulator, which is also why we have, you know, the metal oxide, because the metal oxide is what we use, for the as the insulator. So MOSFET, the MO is metal oxide, and that is used to be the insulator. So the reduction of the transistor size has now, reduced to the point where the distance or the thickness of this insulator is within the high probability jump of an electron from one side to the other side. So just because of quantum mechanics, electrons can now say, I'm going to reappear over here. And that's why we're hitting that interesting limit is, how far, because it's a probability function. Where an electron can reappear is a probability function. So it's not like, if the electron is here, it is not going to reappear over here in real actual distance. It's just that that probability is so low that we might as well just make it zero. Okay? But the effect of going from here to here is high enough that it would interfere with the operation of a computer. So that's kind of the the limit or the technological limit that we're hitting at this point of the history of computing.
Right now.
Right now, exactly. Yep. Yeah, quantum computing is a whole different thing. I sent you guys my note on how I start to study or understand quantum computing. You need a lot more math than you're currently exposed to even understand how things are described. So, so that's a whole different thing. I think some of you will definitely get into quantum computing at some point because all the national labs are starting to do it. IBM is doing it. And even though right now, a lot of people are still saying, oh, that's like cold fusion, it's not going to happen. I think it's just a matter of time.
It's already happened. We're going through the phase where we're trying to figure out our like carry look aheads, our early kind of architecture for it, but eventually it'll start getting like higher level.
Yep. And when it does happen, faster and faster, it's going to be accelerating. Yep, go ahead, sorry.
They actually discovered a new particle using one of those quantum computers where the particle remembers its position in a way, like in space. So like it kind of has like a memory of its own. Like it after like they reset it or something, it went back to where it was without them doing anything to it. Yeah.
I have not studied it enough. Okay, well, I have just kind of chit-chatted enough for this class already. For the rest of this class, for the lab, I just want you guys to continue to work on your program from Tuesday. So you can stay here if you want to. If you have been working on that program, you hit a snag, I can help take a look at it. If you think I can do better when I'm by myself, working somewhere else, that's fine with me too. So there's no structured lab activity for today. It will just be me, being available to help anyone who needs that.
More like a